Welcome to lecture number 16. It feels very much like in the peak of Corona times because the lecture hall here is absolutely empty and there's just one Zoom person. But I had a very good reason for being absent last Friday, which most of you know, and for the others, it's a secret at the moment. We've been talking about Noether's theorem, and we did the so-called no-nonsense version. And that was based on an observation that when we derived the equation of motion for in this case, field theory, but it also works for point particle mechanics, then you have, so you vary the action, and then you rewrite in a certain way, and then you end up with something multiplying the variation of the fields, and something that is a derivative, and then the variation inside. And all of this is under the action integration, for x in our case. So, and with this derivative here and the integral up front, this can be turned into a surface term, the surface of a region of space-time, and then all of this is evaluated on this surface. And then we just claim, or we just consider variations delta phi that are 0 on this surface, and then all of this disappears. And then we say inside omega, the variation does not disappear. In fact, it's completely arbitrary. And we set everything to 0 by this principle of stationary action. And so if this is arbitrary and it should be 0, then this has to be 0 in the end. So and then this leads to whatever is written here is the equation of motion, and then set it equal to 0, and it's that. And now looking at this, if you know that the equation of motion are satisfied, or just consider the case where they are, then this disappears, and then the variation is this divergence, a four divergence, a divergence something. This mu index is contracted with something inside here. And that's interesting because the variation of the Lagrangian, the variation of the square bracket, using the equation of motion is always a four divergent. So if for some reasons you had a variation, a very specific one, where the variation of the Lagrangian is also a four divergence, but without using the equation of motion. So we said, hey, if the variation of L is some four divergence, some F, and here this is a particular, so delta phi equals to symmetry. So this is a definition. If phi, we call phi a symmetry if this works without using the equation of motion. And then here for any variation, this is d mu, and then there was dl. Now, if you really look up what this was dl by d mu phi delta phi, like this. So that's what it always is. And then we can read it from the left to the right. So this is equation of motion, but always for any variation. Then this underneath, inside these parentheses, and then we end up with d mu of dl d mu phi delta phi minus f mu equals 0, and then we call this the Noether current. And that's in principle it. And it suffices for all the computations. But today I want to look at this f and derive an expression what this like always is. Here it comes, at least to me, as a surprise, depending on what is L, what is the variation, and then let's see what comes out, and can I rewrite it in a four divergence fashion. But in fact, you can be very precise about this even in the general case, but you have to spend a few more blackboards deriving this. And that's the goal for today. We will find that this is the variation of the coordinates which can happen as well, times the Lagrangian. In fact, this was the Lagrangian when we considered the translation of the scalar field as an example last time. Let's use a fresh blackboard and do the detailed derivation. And after this, 3 examples for the complex scalar field, one's translations as a symmetry, one's Lorentz transformations as a symmetry, and one's, that's why I picked it, a complex scalar field, the phase rotations to find the charge conservation. In here, we consider now, consider a continuous transformation of both coordinates and the field. So the x mu becomes an x prime mu, and that is the old x prime, x mu plus a little change. And this little change is called delta. I think I write it. Yeah, it's delta x mu. That's a function of x. This is now, this could be any complicated thing, right? Depending on where you are, you could change that location by something different. For example, if you think this is a rotation and you want to move this around, then this point has to be moved up, but this point has to be moved this way and this way. So this could be complicated. For a rotation, this would be a rotation matrix. For example, like this. This is in fact the Lorentz, the infinitesimal Lorentz transformation, where this is the antisymmetric matrix. So depending on where you are, you have a different delta x mu. For a shift, this is just maybe a constant in mu, and then it shifts everything independent of x. But this is general, and all the transformations specified there for the coordinates. And similarly here, we can on top of it not just move the axis. Think of this as relabeling the thing. So this location here in that coordinate has a certain value x, and then you have a different coordinate system, and then that location is very different. It's the x prime coordinate system, and it has just different numbers. So, but then the field hasn't done anything. It's just relabeling of my coordinates. Yeah, what name do I give to the locations? But if I wanted to, I can also change the field. And that makes sense if this is, for example, a vector field. Then so say this vector here points to the left in a certain direction. So in the y coordinate system, it is at a certain location, but it has also a negative x and a positive y component in this coordinate system, x, y. In the other one, it has the new name, the location has a new name that's here, but it also doesn't point anymore in the x prime direction. It just points in the, say, y prime direction. So somehow, although this vector hasn't moved, the components have changed. So when doing something like this could also change or not. Scalar field doesn't change under rotation, but if it's a vector, then it does. And so we accommodate for this possibility by saying, okay, this goes to phi prime, right here, it gets a prime. It's a new location, this is convenient, right? I could also say, oh, well, I'm changing the field. So at this local point, it is something new. But it's easier to express what is the new thing in terms of the new location. Because if it was a scalar field, it would just be this. The scalar field doesn't change. While this isn't true. It changes because of the label. Changes, but this is true. Now, and so I'm choosing this way of writing it. The new field in terms of the new locations is the old one, and then possibly plus something else. Plus epsilon, again, supposed to control the strength of the change, and then here just for it looks the same as a delta. And this could be anything. and we'll see the examples. So this is how it's written. Continuous transformation with epsilon equals 0 being the identity, no transformation. And then everything we do up to linear order in this epsilon. And that's also important. It's not just we don't want to work harder. If we worked harder and did an exact transformation, which is a symmetry, we wouldn't gain anything. We wouldn't be able to derive something like this because there's nothing left. This is the linear term in this variation, and we really want this. So it's not just a convenience, it is a necessity to work to linear order. So first, wiping with that's not the right one, really. Now, the condition for being a symmetry is this. We write S prime, the action, for everything new, L of phi prime, x prime, mu prime, phi prime, x prime, x prime integrated over x prime. So this is everything new, except for the Lagrangian of the theory. What would that be? It's of course the same thing where we plug in everything new, the new field and the new coordinate. But it's the one and only Lagrangian that there's of the theory under consideration. And that's supposed to be equal to the S without all the primes. L, phi of x, mu, phi of x, x, for x. And really, to linear order in this epsilon. At least this is what the linear term of this, so the epsilon doesn't appear on the right hand side because it's epsilon the primes here. So I'm using the linear order in epsilon here essentially vanishes. The zeroth order will be this one, the zeroth order should vanish. Right. This is almost, but not exactly what we had earlier when we said that the Lagrangian here, this new one should be the old one plus the 4 divergence. The 4 divergence here means if you integrate it, it's different from the other side by a surface term. That is not written here. The surface term. So this equal sign is a little stronger than we had earlier. We can weaken it by saying not that it's literally equal, but the variation of left and right is equal, and all the constants disappear. So basically, up to linear order in epsilon and up to a constant, and up to a constant. And those two together really mean that I only want to tease out the linear term in epsilon because the constant doesn't see the epsilon, and I want this epsilon term there. That's really the important thing. And now we'll have several blackboards of derivation to tease out this linear term. The first thing is the integration domain here is omega prime, and this is omega, which really is the same region in space-time, whatever that is. This cloud here is omega, but that is also omega prime as a physical space, but as in the coordinates, in terms of coordinates, it's different. You know, say it's a translation, and this is an interval, say between 0 and 1, and then you move your labels a bit, and then you have an omega prime. It's the same supposed to be the same interval, but it has different labels because you've moved it. Now it's not between 0 and 1 anymore, but it's between 2 and 3, say. So it's the same geometrical thing, but it has different integration regions because you have different coordinates. But since it's the same, I can transform this back to here because at the end I want to compare it, so it's useful and it's important to do the change of coordinates here. So changing coordinates in this integral, change integration variables from x prime, that's the integration variable, to x without the prime, but that is plus epsilon delta. This is what I'm going to do. And let's first work on the change of this is the only work we have to do, the integration measure. Such a integration measure changes by the Jacobian of the transformation. So d 4x prime is this thing. People write it as d. Let's write it as determinant of dx prime mu by dx mu. So I have to write this big matrix, or it's a 4x4 matrix, and then take the determinant, and then I have d for x. So that's the transformation law. Let's do it. So the dx prime mu by dx mu is supposed to be the following. Let's write again what that was. X prime mu is x mu plus epsilon delta x mu. Here goes the 0, 0, 0. So d prime 0 by x 0. Well, one I want to write a little bit more twisted. So it's this by this. And it's d by dx 0 of x 0 plus epsilon delta x 0. This is 1, and then we have whatever that is. We can't know in general. So I write 1 plus epsilon d delta x 0 by dx 0. So this is a function of the coordinates. Maybe it's a constant. If it's just a constant, then we don't see it. It's just a 1. If it's a rotation, there will be something left. Now, upper index here is now 1, and that is 0. So the first term doesn't give us anything, because 1 by 0 is 0, and then we have the delta 0. So here it's d delta x 1 by dx 0. Then d delta x2 by dx 0. And the third one. Here, always on the diagonal, when I differentiate x prime 1 with respect to x1, I get an extra 1. I'm missing the epsilon, sorry. Epsilon, epsilon. And here it's epsilon d delta x1 by dx1. Here, where the delta x0 gets differentiated, there's no 1 term. And then let's write one more, delta x0 by dx2. And there's another one, and there's d delta x1 by dx2. And this is d delta x2 by dx1. And this is 1 plus epsilon d delta x2 by dx2. And here are all the epsilons missing. So this little delta is, capital delta is a small quantity, and I chose to write the epsilon explicitly. And there's always another term here, but it's just too much to write. And now taking the determinant of this, but only to linear order is easy, because there's the 1, 1, and everything else is small. So if I use Laplace's theorem to expand this thing, so then well, I have to basically I have to multiply one of the first rows. Exactly, that's how it works. I have to multiply one of the first row with one of the second row, with one of the third, and so on. So in every row essentially has all these epsilons. So I get generically I get 1, 2, 3, 4 epsilons. I don't want that. I want linear order. So the one saves me that I get anything at all. So in 3 rows, I have to choose a diagonal term. Because I have 1, 1, 1, and then something else. So now I'm lucky that nobody's here to help me. I have to do all by myself. Determinant of dx prime mu by dx mu is, so it's the first term, 1, one plus epsilon d delta x 0 by dx 0. And then times the determinant of this bit. Why is this so hard? Should be easier to see than what I'm doing. Well, I don't know. Let's do it. So I'm taking. You know what? We'll try to make this more obvious in the 2 by 2 case. So that's the structure here, and I want to get the linear term. Zeroth order is this 1 times this 1. So I have 1 plus epsilon. I don't know if this makes more sense. I mean, this makes sense, but do we analyze this easily? So anyway, I'll just do it. That's the first term. Then the determinant of this. The determinant of this is okay also to the linear order because of the 1 in here. So I'm expanding with respect to this. So it's 1 plus epsilon d delta x1 by d by x1 times spot 1 plus epsilon d delta x2 by d x2, and then there's 1 plus epsilon d delta x3 d x3. So this is the diagonal. And now I just have to argue that all the others don't contribute. So if you're here in this bottom part, that was my 2 by 2 matrix, then I chosen the diagonal this times this, with these 2 terms. These off diagonal 2 terms would be epsilon squared. So I don't add these 2 things to my subdeterminant of this 2 by 2 part here. It's only this times this, and it's written here. Now, when we're here, I should have also moved to this place and canceled this row and column, and then I have these two left. But these here are also epsilon squared. This one is an epsilon, so this is an epsilon, I'm sorry, this is an epsilon, and these two each bring me another epsilon, so it would be epsilon squared in total. Because this row here has epsilon, so I don't expand about them, and then this continues. So I don't know if you need to write this out a bit more explicitly, but this would be the only thing that has a chance of contributing, and it's not even, it's already too much because it's lots of epsilons. What I have to expand out this, so I get the 1 and then plus 1 epsilon from each. So epsilon and then d delta x0, dx0 plus, and then the other d delta x3 dx3. And so this can be written a little shorter as 1 plus epsilon d delta x mu dx mu, with the summation convention. That's pretty neat. So that is the determinant, of course, only plus epsilon square. I should have written this everywhere. Good. Where were we? We wanted to change the integration variable. So I'm replacing this thing by this, the determinant. There's 1 times the new integration. Why don't I write this down? So now I have integral over omega on both sides. L, then the phi prime of x plus epsilon delta x. I'm spelling this out because my integration variable is now x. I don't want to see any x primes there. And I have a d phi prime of x plus epsilon delta x. Now the question is, what do we do with this derivative? Here it's the derivative with respect to the x prime. This just means with respect to the argument. So it is the argument. Take this is a function and the derivative of this function with respect to its argument. That doesn't change here. So this is still the derivative with respect to the argument. And here this delta is a delta x, and there could be a little x hidden inside. So it's important to keep that prime. So this is the derivative of a function, and after taking the derivative, I insert this shifted coordinate. And here, comma, x plus epsilon delta x, boom. And now times the beautiful determinant epsilon dx mu x delta x mu by dx mu d for x. So this is the left-hand side. Let's, instead of copying the whole thing, call this s prime and then simplify this more, and then I insert it at the end. Now I think I want to expand this one also in epsilon, because I've done this here and I want to collect all the linear terms. Maybe here. Maybe there. So now I'm going to write L of phi prime of x plus epsilon delta x and d mu prime phi prime x plus epsilon delta x and x plus epsilon delta x. Now, this whole thing, so the first, I want to expand it in epsilon. So the first order is obviously just epsilon set to 0. D find x and x. And now there are several places where this epsilon appears there, there, and there. And I could be very specific and differentiate with respect to this first argument, the phi prime here, and then have an inner derivative with respect to epsilon, which is the same as with respect to x. I can do that very specific, or I just think of the whole thing as a function of x or of epsilon, just whatever it is. This is my L of x plus epsilon delta x, right? That's what this thing is. It has more structure, but it is a function of all. So I want to do all at once. So I'm writing here the epsilon delta x mu d mu L of x essentially. This is what this expansion is. If this was just an f of one variable, then the first term in this epsilon expansion would be the differential with respect to this argument, and then have this shift there. Right? This is how I'm thinking. This derivative hits everything in there. So now I'll be explicit again. So this is my phi of x, comma d mu phi of x, and x plus higher terms. So importantly, this derivative is not just hitting this explicit dependence, but it's hitting everything in it. It's a total derivative with respect to x of this, not just the explicit x's, but everything that is hidden inside. I could have written it all out, but I want it in this form because I want to pull it in front anyway. So this is now it's a total derivative. It's everywhere. It's there and there and there. We're not going to let it hit because we want to keep it outside, but this is what it's meaning. And now this prime here as well. I said this before, it's the derivative with respect to the argument. So if this is the derivative with respect to the argument of this function, well, the argument is now called x. I'm not getting confused if I call this d mu because it's the derivative of that function. So the prime is gone for that reason because the argument has changed its name. And now this is nice, this combination. When you look here, this is epsilon times the derivative of the variation with respect to x, and the variation is here, and it's the derivative of something of the Lagrangian. So the Lagrangian will be when this Lagrangian multiplies that. I have to like 1 times 3 times 1 in a second. I'll see it in a minute. Let's do this now, not in a minute. So S prime is all of this goes in there. This was the first term, and the non-epsilon part is this times the 1. So integral L phi prime x d mu. There I also can skip the prime for the reasons I said. Phi prime x boom. So this is the 0th order term and the 0th order term in this factor, and now the linear term that will be this times this, or the 1 times this second thing. Okay, well, then this one times the epsilon plus epsilon d delta x mu dx mu from there times this lowest order and L of phi prime x d mu phi prime x And from here, the linear term, and then there, the one will be plus delta x mu times d mu L phi prime x d mu phi prime x x plus higher order terms. And then the whole thing, that's my integration, right? The what x. And this is a four dimensions, and this is exactly where we wanted to go. We wanted to get to this f. So an integral L phi prime d mu phi prime and x, and then come plus epsilon d mu, and this is the product go backwards, delta x mu times L of phi prime x d mu phi prime x. That is d for x. So this is so long. It's prime. It's not an important formula, but well, it's a step in it. I just want to make it more visible. And now this looks almost like the term on the right-hand side, which I erased from the blackboard, except for we still have the primes on the phi. So I want to, in order to be able to compare it to S, which is the same thing without the primes, I have to replace these now. That was it's awful determined. Let's get rid of it. That's why I didn't want to erase this thing here. So here it is because it was convenient, more convenient, as I said, to write it as the new field in terms of the new coordinates. Because then, for example, the scalar field doesn't have this term. Very easy to write down. But here I want to change now from x prime at x, from phi prime at x to phi at the same x. So I have to combine basically these two things. So here it says, I'm going to repeat this, phi prime of x prime is phi of x plus epsilon delta phi of x. And the x here is x plus epsilon delta x. So I can expand this thing now in this argument. So this left-hand side, this is equal to phi prime of x, the lowest term where I set epsilon to 0, but then I expand an epsilon just like with the Lagrangian, and then I have epsilon delta x mu, it doesn't matter, mu, and then d mu, and this function phi prime of x plus, and then higher order terms. So I have it expanded this thing like we did. And now there's another step. I want to argue that I don't need the prime here. And that is because the difference between the phi prime and the phi is of order epsilon already, and there's another epsilon. Let's just, so eventually, in just a second, I'll have gotten rid of this prime. Let's keep it for another minute to see that this makes sense. I'm reading this equation now here from here to the side. I'm writing phi prime of x is equal to phi of x plus epsilon delta phi of x. So that's that. And this needs to go on the other side. it was on the left hand side, goes to the other side with an epsilon delta x mu d mu phi prime of x plus stuff that is at least quadratic in epsilon. And so the difference between the phi prime and the phi at the same location x is the difference of them. So let's write the difference. The difference delta phi of x, I'm defining this as the difference between the phi prime of x minus the phi of x. This is of order epsilon. Because you see, if you pull this to the other side, there's an epsilon, there's epsilon squared. So the difference between these two is small, is of order epsilon. And if that's small, then I can insert, I can basically change the phi prime here into a phi, which will change these terms, but not this one. Because the lowest order, phi prime is equal to phi, and there's an epsilon. And the next term, the next to lowest order, will bring an epsilon, which moves the change here. So if I remove the prime, I haven't changed anything. So in this, at this location, I can write phi of x, just messing up the next terms. So then, so this is phi of x plus epsilon terms. And now this difference is equal to epsilon delta phi minus epsilon delta x mu phi plus stuff. So this thing, that's interesting, this is called the total variation, the total variation of the field. Why total? Because it is a combination of what the field changes because the field changes, and what is the change because you have relabeled your coordinates. That's that term. So here that comes in this bit. That's the change of the coordinates. That's the change of the field. And both considered together is this. I think I want to draw a picture to illustrate these two things. I'm just going to waste some time, but spend some time, which I won't have in the end, but there's nobody here to complain. I'll just use the time for a picture. This is not a field because there's too many dimensions to draw it, but let's say I have an x-axis and then I have a function, and I've chosen, I guess I'm choosing this is my field phi of x. And now I'm going to move my coordinates. So this is now the coordinate system. Oopsie, sorry, I killed this. So now it moves to the other side. If this is whatever this is, A, here is 0 in white, and here's 0 in orange, and so this means that the x prime is the x minus A, right? If and here is in red, here is in white, the A. 0 is here and A is there. So if x is A, then I'm in orange at 0. Right? So I've moved it to the other way. Here it's a plus epsilon, but I think I wanted to see it better. I want to move it to the right. So anyway, this is happening here. And what does that mean? If I was first at the origin, the observer, I saw that much field up to here. And now I've moved infinitesimally, right? Just a little bit to the side. So then here, all of a sudden, my field is bigger. It's that big. So it was that. And now it's this additional piece. So that has just This has happened, my field here has become bigger because I moved. That's that term. So it grew, what did it grow by? It grew by the shift minus epsilon. All of this is the shift. With this minus sign, I have a negative shift, so it's plus, it grows by the derivative. So the derivative here is some positive number, and then look exactly what it changed by, right? The derivative times this distance times the shift is what it changes. So this thing here is, in my case, minus sign times minus a times the derivative here. So it's minus epsilon delta x, essentially. Mu d mu phi. So that's the change because I moved. And I haven't done anything to the field because the field is still that curve. If I now wanted to, because I want to illustrate it, I want to change my field as well. And let me change it. What do? We multiply the whole field by 2. Which means if you multiply by 2, then this is the field phi itself. So we add phi to phi. It's like having 2. Or epsilon times 2. So anyway, this becomes bigger. Yellow. So now this is my new field. Phi prime at x what? Phi prime. I don't even know. X prime. Depending on where you want to look at it, right? This is new field which just has doubled, and you can express it in terms of the x or the x prime. And this bit here is delta phi. Well, to be quite honest, to be more honest, it's this. This is delta phi because not even, right? What is delta phi? Delta phi is the difference of the new in the new coordinate system minus. Oh, that's too much. This is my x, this is my phi, so it's this point. The difference between these two, it's really a lot. It's either here or it's here. Okay, so this is the honest answer. Why I was hesitating? I hesitated because I want to call this the total derivative, the total variation, because it's sum of 2 combinations. Now this looks a lot more total than this part, but that's just because of the minus sign in between. So we're kind of subtracting things. I guess you have to think about it harder and maybe not move it to the right, or have a function that goes with a negative slope. But the point is so that the phi field changes, and then the axis change, and then choose another change, and then you pull this all together, and then have started with this. We ended up with this thing here. So that wasn't right. This yellow bit. This is delta phi, and the two together are purple. Is this? So this is delta phi of x. And although it's smaller in the picture, it is the sum of the change of the field phi, so the delta phi, and the change because I shifted it. These two together with the right minus sign gives a total shift. And that is now the difference between what the field phi was at the location x before and after. Right, so this little delta x is the change of the field at any single location. The big delta is the change of the field, but comparing different points. And then this extra bit does the motion, right? All right. Why am I doing this? Because I want to change this now into something without the prime. So I have to expand this one more time, and now using that. L. So let's collect phi prime of x is phi of x plus phi prime of x is phi of x plus delta phi of x. With the delta from here, I'm not going to erase. And this goes in here. The derivative changes like this. Derivative of this function with respect to its argument, d mu, is phi prime of x, and it's d mu phi of x plus d mu delta phi of x, just taking the derivatives. And now, this goes in here. L of phi prime of x, d mu phi prime of x, and x is equal to, we've done this when deriving the equation of motion, so these steps are, and so the zeroth order is L phi of x mu phi of x x. Now comes to first term of the expansion. It is d L by d phi, taking the derivative with respect to the first argument. And then L has all these arguments, and I'll bring that out, and then the variation delta phi plus with respect to the second argument, and then times the variation mu delta phi, and then plus nothing else because I only go to the linear order. So this L is now these three terms, and the L sits here and there. Here I have to write all three terms. Here I don't have to write. Here I just write the first term because there's already an epsilon, and these variations were proportional to epsilon, as we said. So now I really write on a space. Venus, S prime is integral. Now all three terms, L phi of x, d mu phi of x, x plus dl d phi delta phi. The arguments are the same, plus dl d mu phi d mu delta phi. That's the first, and now comes plus epsilon d mu, and in here I have delta x mu times L, and L has the primes, but as I just said, in the expansion, I only keep the first, because this is already a correction term, and then since the argument is always the same, I'm not going to copy here either, and that's that. And then d for x, and this is supposed to be s, which is really the first term. So we're ending up, if I subtract from this side this s, which is this, then I have 0. So 0 is equal to integral this. if let's just spend the time. Copy it, d phi delta phi plus dl d mu phi d mu delta phi plus epsilon d mu delta x mu l d for x. So this is all zero. And here now the same with the equation of motion, pull this out and subtract basically integration by parts the other way around. And the other way around fits nicely underneath here, I guess, if we relabel our mu to a nu. So that yeah. So let's do it. This is equal to 0. It's equal to the integral d L d phi minus d L mu d mu phi all times delta phi. That's the term where the integration hits now the other factor, and then comes a plus with the d mu on both d L d mu phi delta phi. Yeah, and now plus epsilon, and this is now mu, and then we have delta x mu L, parentheses, another parentheses for x. So, and let's see what we got. This is what I sketched in the beginning, right? We have some term that looks like the equation of motion, and some that is the fourth derivative of something else. But here it's very concretely this term rather than a random f term. That's essentially what we call f before, or really minus f. The integration is over the region omega, and that is just some region. And you might wonder, can I set this to 0 really? What about the boundary terms? We had a region omega where we said for deriving the equation of motion that this thing is equal to 0 only if the variation on the boundary is 0 and all that. So can I really use the equation of motion here? And the answer is yes, because you're supposed to think of this omega as being much smaller, very small in general, like almost local in comparison to when you derive the equation of motion. That's really the global thing. You want it everywhere. You integrate over the whole space, and you have these little variations which test what's going on locally. Here we're deriving a conservation law, which is this conservation law of the current, and it's very local, right? It's d mu j mu equals what's flowing there. So locally we have the equation of motion. So think of this as arbitrary, but think of it as small. Then certainly you're within the region of where the equation of motion holds, and we are able to set this to 0. And then for this small region, we have this conservation law. You can also do the integration by picking here the time and the space separately, and then really get the charge, the conserved quantity out of it, the zeroth component of the current. Yeah, then you're there. Or we just keep it local and just say that's 0. And that's what it is. And now I can. So it looks like this. So you have your big universe, omega, that's chosen for the equation of motion, and we are working within. So here's my little omega, basically. This is the omega that we're using now. Noether, Noether like this, and this holds, so this is 0, and then we have the equation, the integration of this little omega over this is 0. But that is an arbitrary surface. We can also, or volume. We can also use this and anything here. And so if for any surface that you, sorry, not surface, for any volume omega that you choose here, you have the same thing. It really means that this has to be zero. So d mu dl by d mu phi delta phi plus epsilon delta. Yeah, my delta's away. It's fine like this. I didn't make a mistake. It's notationally like maybe a little inconvenient. It would have been really clever had I written an epsilon in front, so defined what everything, what's called delta phi is really epsilon delta phi. Then it looked nicer because an epsilon here, epsilon there, but okay. It'll all be better if I now insert this delta in here. You see what I mean? What I'm kind of sad about is that this can be anything, and the epsilon makes it small, and this is small just because there's an epsilon in it. It would have been cute if there could be also anything, and the epsilon would have been telling us, oh, this is small. Now, this epsilon delta phi, now there's the epsilon minus epsilon delta x mu d mu of phi. And now we shuffle this a little bit. Now I can divide out the epsilon really. The first term is mu phi delta phi, right? By epsilon, divide by epsilon, then we have this, and then comes minus multiplying by this object, it's dl d mu phi. Now this, there's the minus sign, epsilon's gone, then we have this is now, let's call this nu because it's mu delta x mu. So and then this equals 0. I'm still inserting this, but let's just verify that that works. The first term is this times delta phi, and the second term is really that times that, where I relabeled, let's do it here, mu because the mu is already there. And then the derivative was here, the delta goes to the back, epsilon is divided. And now inserting this one as well, and I wanted to have this principle. I'm going to pull out the change in x there. It's a mu, and that can't be changed because the mu is connected to that mu. So I have to keep this in mu. But since they have the function that I need to have a delta function, so it's a delta mu. These two together makes an x mu, which I need. That's L, and then the sign, because I pulled out the minus sign, is plus the minus sign. Boom. That's this. You know, since this is super lovely, let's write it like this. We have J, we have D mu. I'm really copying the same thing. And D mu. There's a conserved current. The current has this form. The derivative with respect to the derivative of the field and the variation of the field. So if the field changes and just the field changes, then that's your current. That would be, for example, the phase rotation. You don't move your coordinate system, you just rotate the phase, the complex phase of the field, then that's all it is. Or if you change the other thing, then you have minus dl by d mu phi, which is the same as here, but then the derivative minus delta d l delta x mu. If only the coordinates change, for example, the translation, then we have only delta x equals non-zero, but the field doesn't change, and then this is your current, and then you can also have both. And that's it, and that certainly needs the box. Are there any questions? One person to ask. Otherwise I'll discuss the three examples. The translation, which only gives us this term. The result will then be that expression in parentheses here is the energy momentum tensor, because the current corresponding to the charge corresponding to translations is energy momentum, and then the current is this energy momentum tensor, the one that we had last week or previous lecture. Then the second example is Lorentz transformations, which includes the rotation. So we have a change in x and a change in phi. So we see both terms. And then the charge will be the angular momentum and the boost charges. And then the third example will be just the phase rotation, just this term and not the other. That will be the three examples that I would like to discuss. If I go over time, nobody's there to stop me. Example, complex scalar and in translations. See how we write this all down. The delta, the x prime is the x plus a little bit. So let's have the Lorentz in x plus an epsilon and a little bit. And let's say the a mu is a 4 vector and it parameterizes the translation. It gives us lots of choices. You can pick another vector. It's not just a parameter epsilon, which is the strength, but you also have a direction. So essentially, this is 4 linearly independent sets of continuous transformations for the 4 different directions. And nothing happens to a scalar field under this. So here the delta x mu is this constant vector A, and the field phi prime of x prime is phi of x, nothing else, so it means delta phi 0, and then now we can use the formula which immediately gives us the j. The complex scalar is we have to have the Lagrangian, so it's d mu phi star d mu phi minus m squared phi star phi. And so what we need is this derivative dl by d mu phi. Yeah, that's a good point. I didn't say that yet. In my derivation, I pretended there's only one single field. It could be more than one field, and then you would have to have an index. But you do everything for all the fields. So if there's many fields, then you have many variations, and then we have many derivatives. Oopsie, that should be right. So in here an I, and there an I, and these are summed over. That's it. So here in the complex case, I have two fields. So I have to have this thing, and that is d mu phi star, because I take the derivative with respect to the d phi mu with index down and up remains. And the other one is d by d mu phi star, and that is d mu phi. So I have both fields. So in this sum, I have both of them. Here there's nothing because the phi doesn't change under rotation, under translation. So So my current J is minus sign. And then the first one, mu phi star. Now the variation, the derivative of the first field. The first field is this, I have to look down here. It's not the phi star, which ends up there, but the one I differentiate with respect to. So it's the derivative here, and the index is always down, du phi. Now the next one comes with the plus because of the sum, and then d phi times du phi star is the derivative with respect to the of its conjugate. There minus delta mu times the Lagrangian, and that is this. D mu squared kappa phi star d kappa phi minus m squared phi star phi. Boom, boom. And that's the current J. That's it. That's just what it is. And I can't simplify it. This delta is missing. The index, so there's a delta x, and the delta x is this A. I need to write an index mu, so this is A mu. Right, so that's really it. We have one index mu on the left hand side, and we have one uncontracted index mu on the right hand side there. Everything else is contracted. But since I can do this for any direction here, it really means for all mu, this is a conserved current. I can actually call this here. I feel like I've said this last time. For every mu, so it gets a 2-index thing. And for some reasons, I like to pull this index up, so the nu goes up everywhere. And then we have d mu phi star d mu phi looks a bit more symmetric plus d. Now this way or the other way. Let's say mu phi star d mu phi. I've changed the order. The star is always in front now. Minus this when we lift, then you have a eta, the metric, delta phi star d kappa phi minus m squared phi star phi, and that's it. And it looks nice. Now it's manifestly symmetric in mu and nu. The symmetric version of this is this, and it's symmetric. And that's what's called the energy momentum tensor. Let's see what the charges are. So the energy, always the charge. So charges is always the zeroth component of the current integrated over space. And here I have 4 currents. And the one where this is the 0, it's the energy. So my D00 is the energy before integration. So it's the energy density. Let's just write it as the energy. Energy is H. Hamiltonian is the energy. Is this integrated over all 3? And so something happens when I set both of them to 0. 0 here is just the time derivative. So I'm getting integral dx, and then I have a time derivative here and there. And that's the same terms. I have 2 of them. And then I have minus, and eta 00 is +1 in my convention. And so then we have this term. This is phi prime star phi, phi dot star. And the spatial component are negative, so minus phi star scalar product phi, and then there's minus m squared phi star phi, boom. And now these parentheses, this minus sign makes everything positive in here, and 2 minus 1 is 1, so if I end up with dx phi dot star phi dot plus gradient phi times gradient phi 1 with a star plus m squared phi dot phi star phi. This is my expression for the energy of the field. And what is nice to notice is that it's all positive, these are squares. Absolute value squared of the phi dot, absolute value squared of the gradient, absolute value squared of phi itself. So this is certainly positive, it's only zero, there's no field at all. As soon as there's a little bit here, it gives you something. So there's nothing negative. This is the good news. When we had the Klein-Gordon field earlier, in the very beginning, we had sort of negative energy solutions, but it was a different energy. It was just, think of it as a like single particle quantum mechanics thing where you had a Schrödinger equation. So when you interpret the Klein-Gordon equation as a Schrödinger equation, then you get negative energies, but that's not what we're doing now. We have a field theory and we have a Noether charge, the energy, and it's always positive. That's good. That's good news. Now, the spatial part, maybe the pk momentum. Let's write pk is integral t0k d3x, and that's integral d3x, and 0 on one is phi dot, and the other one is a derivative dk phi, and here plus. Let's pull this again to the front. So it's phi without the dot, without the star is a dot, and then we have a dk phi. This, and there's nothing because mixed indices don't give us anything there. So that's our momentum vector. If you remember that d with the upper index mu was dt and minus the gradient, then we end up with the vector p vector. This is well, the p mu is h and p vector with the upper index, but the derivative has the minus sign, so I get a minus sign. So minus integral d3x phi dot star gradient phi plus phi dot gradient phi, and this is start missing right there. This is the momentum. There's an oh, this one, no, don't want it. What else? We're still time. Oh, we're not. Oh, maybe. I have two more examples, and someone calling me on Sunday. Are you crazy? Now, example, complex failure and lower differentiations. And then we have the delta, so the x prime is x mu plus epsilon. Also, let's be why not? Let's write the whole thing. Just yeah, let's do it. So it's e to the I half omega alpha beta m alpha beta, and then acting on x, and the whole thing has index mu. So this thing has indices mu mu x mu. That's now not a small transformation. It's really any big given by this. Let's make it small, and we stick an epsilon in there to control it, and then expand it. Epsilon equals 0. This is x mu plus the epsilon terms epsilon I half omega alpha beta m alpha beta mu mu x mu plus square terms. This thing we had at some point, the representation on the four vectors is the eta alpha mu delta beta mu minus eta beta mu delta alpha nu. And then, it's equal to x mu plus pi epsilon. The half goes away because this is anti-symmetric. Let's write those both. Write both. No, right. Okay, 2. This becomes beta, and the alpha is a mu. We have another term where the mu is the alpha, so it's this mu, and the mu is here, and all of this is x mu. But I don't like this up and down story, so this goes up and this goes down. So nothing changes. X mu plus I half epsilon omega mu minus omega mu x mu. And now you see what I meant. Since it is antisymmetric, I can turn it around with the velocity of twice the same thing. So it's mu just x mu, and I forgot an I, right? I times I is minus 1. That looks better because now it's real. What would be the world if you rotate, Lorentz rotate, or just rotate internally? Minus epsilon omega mu x mu, and everything is real. And since the scalar field, the compass or not, there's no change there. So delta phi is 0, delta phi star is 0, just like it was before. And this thing is delta x mu. So the difference between the translation and here is that the translation had delta x, which was constant, and here the delta x isn't constant, but it is proportional to x. This formula now what else can we get? J mu is equal to minus the dl is what we had. It's the d mu phi star, and the derivative of its field then plus really the same. It really is the same. So let's not work too hard. I guess all of this is what was the energy momentum fields, right? It's what we have right there. So I can just do that. We had the minus sign of the energy momentum potential mu. That's what it is, and then times the delta x mu, and delta x mu is minus epsilon omega, and now I want an x mu, so the mu has to be a mu, omega mu, and then the other one needs to be the mu, it's rho, and it becomes rho. Boom. So it is equal to epsilon omega mu rho times t mu x rho. And earlier with the translation, we had an our j mu stuff and then an a mu at the end. And then we decided, okay, let's extract many currents. And we can do the same here. Here, this is the parameter that tells us in which direction we translated. And this is the parameter, or set of parameters, which tells us about which axis we are going to rotate or boost. And so I want to strip this off, and I want to call all the rest my my current for the Lorentz transformations. But I can't just strip this off because this is antisymmetric, and only the antisymmetric part of this product enters here. Like the antisymmetric part of this. If this is symmetric in mu and u, then it is killed in this product. So if I don't see that, so I can only have the antisymmetric part from here. So this is what I'm going to do. I'm going to write this as. And by the way, where's my index? Why do I have two news up? That's also a bit crazy. I want up. Oh, because it is here, the T. The T needs to go down. The T needs to be down. All right, this is what it was. Here I lifted it up, and this needs to be down, and now it actually makes some sense. Makes a lot more sense. Thank you. I'm antisymmetrizing it, and then we have epsilon half omega mu rho, T mu x rho minus T mu rho x mu. And now I can pull this all out, and I can call this, if I wanted to, my current m mu rho, or I say the current. And so this labels which current it is. It is the specifies which rotation I do, and this is the index for the current. There's many currents. You can leave it up and down. That's not so bad. And it makes a real difference. So I have mu equals 0, many of them, and good. And now I can also talk about which ones they are. There's also some sign, even a factor ambiguity, because the current is conserved. If I have 12 of these m's, they're still conserved. So, or negative of m is also conserved because I can. It's a linear operation here. I can multiply this by anything, and so we have a prejudice of what the angular momentum is, and it's really the minus sign. So I want to define this as minus it. You wouldn't know from just looking at it. Now, so my charges m mu rho are T mu, turn it around, rho x mu minus T mu x rho. That's my current, and let's just discuss the angular momentum, because there isn't any time left really. Well, the angular momentum is the spatial part of this. So I have m 0 because I'm looking for the charges, and I want to integrate it. And then angular momentum means spatial. So it could be ij. And then this is the angular momentum ij. Let's call it ij. And this is Vx T 0 J X I minus T0 I X J. Now we do need to look at what the T0 was. T mu was d mu phi star d mu phi plus d mu phi d mu phi star minus eta mu L. This I don't need because I have only time. Yeah, I don't need it because this is these two indices in this time and space, so I don't care. And here I get the derivative. So it's equal to integral d x time phi dot star d, and the next one is downstairs j acting on phi, and then behind is the next I. The second term has the star put to the other side plus phi dot d j phi star xi, and this is the same as this with I and j changed. So minus phi dot star d I phi xj minus phi dot d I phi star x j. And then we like to hold this index up at the cost of minus sign, and we write it as xi dj minus, and pull this up, xj di. Yeah, this is just nuts, but anyway, phi from here, and then plus the other order, plus the star under that, phi dot xi dj minus xj di phi star. Yeah, I don't know if you care enough about angular momentum to keep pushing this. Let's say you do, then we make a vector out of this. Now we have a j vector that's 1/2 epsilon ijk times this j ij ek. So making a vector, then you will probably see your favorite angular momentum thing. So j vector is 1/2 times epsilon times this. What we have in here is an xi dj ek comes from there, and an epsilon ijk. And this is just the cross product of x vector times the gradient. That's why I raised the index on the x, because the x as a vector has the upper eyes. The nabla as a vector has the lower components, and that doesn't care. It's just a vector. And so that's that. And therefore, I have minus 1/2 integral d to x. I can also get rid of the phi dot star x vector times nabla on phi, that's this term. Then minus basically the opposite, but ij is also antisymmetric, so I get the same thing, cross out the 2, and then I have this left plus phi dot x vector times gradient phi. Boom. So there is your angular momentum. And if you remember, okay, angular momentum in quantum mechanics was r cross p or x plus p, and that is x cross minus I h bar if you have quantum like operating, and that's basically right, your x, it's there again. The factor, as I said, doesn't come out of the theorem because it's still conservative. There's a different factor. My last example I'm going to skip because I'm overdue. Am I? Yes. It was the phase rotation. It's very simple because just the first term and no messing with this momentum tensor. Right on the, you can find the right on the connection. So if there's a phase rotation, then delta x is nothing, and the phi gets multiplied by phase, so this is like a scaling with a complex number, with an imaginary number. So that's because e to the I alpha was an expansion 1 plus I alpha, and that's that. And the complex conjugate is minus I alpha phi. Complex conjugate, and then you get two terms, and the current after some computation is I dot star I minus 1 star I dot. And if you remember, maybe this is what we had as the charge of the Klein-Gordon equation, and it is conserved, but it isn't necessarily positive, but it is conserved. And we interpret it now as the charge and not as the probability of finding the particle somewhere, because as a charge, it may as well be negative and we're still all happy. Speaking of happy, are you happy? Single Zoom?
Yep.
Yes. All right. Thank you for being with me. It wasn't quite as lonely. And I hope next week everything will be back to normal. Thank you very much. I'm stopping the recording.
Okay.